Hello everyone, today I will briefly introduce our project Chip Design using RISC-V Instruction Set Architecture. I am Kenan Postallı, team leader. Our team consists of Onat Bulut as the system engineer, Deniz Özgür Özer as a hardware engineer, Müslüm Akbalık as another hardware engineer. We are developing a processor based on the RISC-V instruction set. Our design includes a UART peripheral and a 4 KB level 1 cache. One key challenge is ensuring the processor boot program counter points to the main memory and configuring the cache to handle data only from the region. We will use test codes to verify the instruction set functionality and evaluate UART performance. In modern embedded systems, we need compact, low-power processors that can efficiently handle data. Traditional solutions are often power-hungry and complex. Our design addresses these issues by providing a resource-conscious, high-performance processor that balances data handling, efficiency, and power consumption. Our processor will support the RISC-V instruction set architecture, UART, PWM, and SPI peripherals. It aims for high performance with low power consumption, compatibility with RISC-V tools, and modular design for future scalability. Our concept is a scalable RISC-V processor with efficient external memory and peripheral data handling. Designed using Verilog and System Verilog, it ensures modularity and flexibility. Testing in simulation and FPGA environments will confirm the design's functionality and performance. Also, you can check the level 1 design here. Thank you for listening. Now I will pass the presentation to Dennis, who will continue with detailed explanation.
Hello, my name is Deniz Özgür. Today I will talk about implementation details. Our design encompassed RISC-V processor core, some instruction set extensions, and some peripherals. All of them connected through the wishbone architecture, and we use memory mapping to data transfer. RISC-V has core instruction sets that inherits arithmetic, logical, and control instructions, and the extensions are multiply, divide, atomic, single precision floating point, bit manipulation, control, and status register. We use pipelining to improve instruction throughput. It allows multiple instructions to be processed simultaneously. It reduces overall execution time. We have databed that consists of program counter, register file, multiplexer, arithmetic logic unit, and our control unit is orchestrating them. We have VGA controller interface that operates in text mode. It utilizes a font bitmap to render characters on the screen. Each character is represented by 16-bit data structure, where the first 8 bit is correspond to the character code, the subsequent 4 bits is foreground color, and final one is background color. It generates horizontal and vertical sync signals to the control to refresh rates. Serial peripheral interface has high-speed serial communication, and it communicates with external devices such as sensor, memory chip, and other microcontrollers. It has both supports master and slave modes. It allows flexible communication configuration. It implements full duplex communication. It enables simultaneous data transmission and reception. Universal asynchronous receiver transmitter enables that asynchronous serial communication. It allows processor to communicate external devices like computers or other microcontrollers. We have also configured the baud rates in UART. Last one is PS/2 keyboard interface. It captures scan code from standard keyboards and it memory maps to our memory.
Hello, I'm Onat Bulut and I'll be presenting our testing strategies. We have divided our testing in three parts: module level simulation, hardware testing, system integration testing. In module level simulation, we have tested individual modules in software simulation environments to ensure they work as expected on their own. The major parts in these tests were the arithmetic logarithmic unit, multiplier divider unit, floating point unit, hazard control unit, memory bus controller, and pipeline and control logic. In this slide, you can see our division unit performing a non-restoring division. The dividend is minus 5463 and the divisor is 32. As expected, the result, which is the quotient here, is minus 170 when the down signal is asserted. After testing the modules in software, we have tested them on the Nexus 4 DDR FPGA. These tests mostly consisted the testing of interface units, UART, SPI, VGA output, and the USB PS2 keyboard. Here you can see the VGA interface in action, printing random characters on the display. Lastly, we have system integration testing, where we tested the whole system by running applications on the processor. Here's a simple program that initializes two registers, calls a 10-cycle delay, and does store-load operations successfully.
Hello, I am Müslüman Balık. Firstly, I will talk about the cost analysis of our project. In our project, we used FPGA board, a logic analyzer, and USB board converter model. As the main FPGA board, we used the Zybo Z7, and as an alternative, we used the Nexus A7 FPGA board. Now, I will talk about the commercialization of our project. The most important feature of our processor is it is low power consumption. In addition, it has 6-stage pipeline architecture, 4 kilowatt Li1 cache, and UART, SPI, Vega, and PS2 keyboard modules connected through the Wish1 mode interface. Our design can be used by embedded system developers, IoT device manufacturers, and most importantly, people working in academic research. If we talk about the use cases, it can be used in academic research, wearable technology, military systems, automotive systems, and smart devices in various sectors. And now I will talk about our commercialization strategy. We plan to license the processor core. We develop it as an IP core that can be integrated into products by different companies. We will also offer technical consulting services for custom system design, IP integration, and optimization. To make it easier for users to integrate the IP core, we will provide detailed documentation and helpful development tools. We will also create a complete online portal where users can access all documentation, community support tools, and sample project. In this slide, I will talk about how we made our project follow standards. First, about safety. Our low power design does not get hot, which is good for both the device and the user. We also have safe error handling and control register use. In parts like UART, we stopped problems like buffer overflow. Second, we cared about user and environmental safety. Our design follows EMC rules, so it can be used safely in home or industrial device. Lastly, our project follows ISO standards for safety systems. In the future, we plan to get CA, FCC, and RoHS certificates. In this slide, I will talk about certification and safety. Our processor follows the RISC-V rules. All instructions we are tested in both simulation and on the FPGA board. Units like UART and SPI use standard protocols like RS232 or SPI Mod 0. Vega and keyboard support PS2 or USB-based design. We use the Wish1 bus, which is open standards. The design also works with open source tools like LightX and OpenCourse.